We talked about, very briefly, some ways to determine whether or not our model is making good predictions. But another thing to be aware of are data points that could be impacting the accuracy of our model, how well that linear pattern fits with our data. Any data set can have outliers, data values that are extremely large or extremely small. In the case of regression, outliers are points that don't fit into the pattern, that linear pattern that we're looking for, as well as the other points do. We call these influential points since they greatly influence the resulting model and the pattern that we see in the data. In example 4, we have a table that provides the CO2 emissions in metric tons per capita and the life expectancy in years for different countries. And what we want to do is construct a regression model for this data and interpret the slope. I have the data entered in, so we'll construct that linear regression model. The first thing to note here is that our value for R, that correlation coefficient, is a little bit less than 0.6. So we're still closer to 1 than we are to 0. But that means this association that we see between these variables, which we could go ahead and zoom and see that pattern, is not as strong as we've seen in some other cases, but still pretty far from 0, so not weak. And we have our value for M, our value for B, meaning we can construct the regression equation y equals 0.8255x plus 65.4513. With that value for R of 0.5928. Interpreting at our slope tells us that if our value for X were to increase, so if CO2 emissions increase by 1 unit, so by 1 metric ton per capita, then our Y variable, life expectancy, would increase by 0.8255 years. So let's pause here for a moment from what this problem is actually asking us to do and talk about what this is saying. This is saying that as countries pollute more, release more CO2 emissions, life expectancy in that country is actually increasing by a little bit under 1 year for every additional metric ton. That doesn't make a lot of sense with what we understand about even simple things like air quality and health. So there is probably a lurking variable that's impacting these two variables, causing them to increase together. My guess would be something about the wealth of a country. As countries are wealthier, maybe they have more cars, more industry, they're producing more CO2, but also they have better medical care. So even though something like air quality might be affected, health is improved in other ways. So this is very likely not a cause and effect relationship. CO2 emissions don't make people healthier, but those two variables do increase together in the same direction. Now what we want to do is go back to that data, back to that scatter plot, and identify any influential points. We can see a few. One, for instance, at 0.64, 51.86, this low hanging point that's very close to the y-axis. That's Nigeria's CO2 emissions and life expectancy. We have a couple others, the United States with CO2 emissions at 17.96 and a life expectancy of 78.24. That's this value that's pretty high above our line of best fit. And then Russia's emissions at 12.04 and a life expectancy of 68.8 is hanging a little bit below that line. Determining outliers is a little bit up to subjectivity, but what we're going to do is go ahead and delete some of these data values. So we're going to delete the values for the United States. We're going to delete the values for Nigeria. And we're going to delete the values for Russia. Got to go back and delete one more time to get rid of those empty rows. And we're going to look at what happens to our model and our correlation coefficient. Just looking at this even visually, we can see a much tighter pattern, and that's supported by our value for R, 0.9059. So when we deleted those three influential points, we get a much stronger correlation coefficient, and we get a new model, 1.707x plus 66.018. So the important concept here is that removing those influential points gave us a much, much stronger value for R, a much stronger association between those two variables. But the lingering question, the remaining question, which is subjective and based off the data we're considering, is if it's appropriate to remove those outliers. In this case, likely not, because these were actual data values that were collected for these countries. So they don't fit the model very well, but eliminating them just to get a better model is a little shady, a little suspicious, kind of makes it seem like we're modifying the data just to get the answer that we really want. In a different situation though, an outlier could represent something like a data entry error. Like let's say instead of 17.96, this was 1,796. Well, that number is massively larger than any of the other values in our data set. So, and since we have the original value here, we can see that what happened is someone just made an error entering that data. Should have been 17.96 instead of 1,796. So it's important to look at outliers, understand what they suggest, if it's a data entry error, if it's something that doesn't fit the pattern but is an authentic data point, and then whether or not it's appropriate to remove those just to get a better fitting model. Again, it really just comes down to the situation, and that's why we have statisticians and people who analyze this information and think critically about these different kinds of results.